So first in this presentation, I'm going to try to give you like kind of an intuitive explanation of how behavior trees work, since throughout the project we've been using behavior trees, and it might be nice to know how it works on a more theoretical level. So that's what I'm going to do first, and then I'm going to go more into depth on this paper that I just talked about and what the contributions were and how it works. So here we go. So behavior trees briefly. What you see here is a tree. That's a behavior tree. It's really complicated. You don't have to understand how it works, but what you see here is that there's a bunch of green boxes. Those are low-level controllers. And then at the top, you have a blue box. So what behavior trees are essentially is it's a method to combine a bunch of low-level controllers that can be used for any sort of individual task, and combine them all together into one high-level controller, which is basically a controller that decides which low-level controller to use based on which situation you're in. And the reason why behavior trees are preferable for a lot of robotic systems is that they're optimally modular. And this has actually been shown theoretically recently, actually. So the claim that behavior trees are modular is not just hand waving, it's actually theoretically true. And the reason why modularity is really important is because modularity reduces complexity. And we know in an AUV, there's lots of different subsystems that interact with each other in different ways. And reducing complexity helps to reduce the cost of both development and testing, time, money, and it also makes it more explainable. You can understand how the system works more intuitively. So that's in essence why we're using behavior trees in this project. And here you can see SAM. You're all familiar with SAM. It's the AUV that we use in this project. And it's an example of a cyber-physical system that's really complex. Right, so now I'm gonna try to explain to you how a behavior tree works. So here on the right, we have an example of a behavior tree for a situation that you might encounter in your home or apartment or wherever. Say you want to eat food. You need to go to the kitchen to eat food, and you also need the lights to be turned on to eat food. So what this behavior tree controller does is it allows you to achieve all those goals in order for you to eat food. So the colors I've used here help to highlight this relationship. So each one of the low-level controllers here in green, it gives a metadata feedback. So while this action here, go to kitchen, is executing, it will tell the rest of the tree, am I succeeding, am I running, or am I failing? If the action's running, it means it's doing its action. If it's succeeding, it means it's achieved its goal. And if it's failed, it means it's failed its goal. So basically each action returns this metadata to the high-level controller at the top. And then that controller determines which one of the other low-level controllers to use. And that determination is done by these so-called compositional nodes. So on the top here, we have a sequence, which is indicated by the arrow. And then in the middle, we have a fallback. And now I'm going to explain to you how those work. So again, I'm using colors here to help you see the correspondence. So in green, we have a sequence on the top. So the sequence ticks its next right child if its previous left child was successful. So if go to kitchen was successful, then the sequence is going to tick the next action in the tree. And similarly with a fallback, in the opposite way, a fallback is going to execute the next child if the previous one has returned failure. So if turn on lamp A fails, then turn on lamp B runs. And yeah, if there's no other children, then the tick gets returned up to the tree. And each one of the nodes can also return running. So basically how it works is if go to kitchen succeeds, I'll explain it on the next slide. Yeah, so now I'm going to explain to you how the behavior tree works in the form of a decision structure. So we start with node 1, which is go to kitchen. So if we're successful at going to the kitchen, then we're going to go to the next action, turn on lamp A. And if lamp A fails, then we're going to go to action 4, which is turn on lamp B. If it succeeds, then we go directly to action 5. And so you can see there's 2 different paths for you to get to action 5, which is eating food. You can either do it by turning on lamp A or lamp B. So there's 2 options there. And yeah, also each one of the actions, they can return other statuses like running or failure if there's no composition node to redirect the return value. Right, so now hopefully you kind of understand how behavior trees work a bit. So now I'm going to go into what we did in our recent paper that got accepted to the IEEE control systems letters. And that's showing that these behavior trees can actually be formulated as discontinuous dynamical systems, which gave the following contributions. So it was the first continuous time formulation of behavior trees. We proved that behavior trees can be interpreted as discontinuous dynamical systems. And through that, we were able to determine or prove the conditions for existence and uniqueness of behavior tree executions. So guaranteeing that the trajectory of your system under the behavior tree controller is actually unique, like you can actually analyze it. And then with these behavior tree controllers, we also prove the conditions under which they would make the system convergent. So like, say you have like some AUV mission you want to do, and it involves multiple different tasks. We proved that a behavior tree controller with a bunch of different subcontrollers could be convergent to an overall goal involving multiple subgoals under certain conditions, which you can see the paper here for more detail on how that works. But now I'm going to give you kind of like try to give you kind of an intuitive understanding of how it works. So this is the decision structure we had before. And yeah, as I said, there's like multiple different paths for you to get to action 5. And actually for each one of the actions, there's different paths you can take. So, but let's just look at action 5. So we can either take this path here, or we can take this path here. And so given those paths, we can actually determine the necessary conditions for each of those controllers to execute. So in order to execute controller number 5, we need to have controller number 1 succeed, controller number 3 succeed, or we can have, these return statuses. So altogether, those give us the necessary conditions that we need to execute the actions. And so with those influence regions, they're called influence regions, we're able to determine what we call operating regions, which are the regions of the state space that are sufficient to know that we're executing a low-level controller. And so as you see with the colors here, this corresponds to being both in the influence region and in the regions given by the loops there in the colors. And so with that, we're able to formulate a discontinuous, or we're able to formulate a hybrid controller. So say we have like some dynamical system where it's just a function with the state of control and it returns the rate of change of the state. So an AUV can be formulated that way. Then we define the execution of a behavior tree as the simulation of that dynamical system with the behavior tree controller, which is this ordinary differential equation here. And and using those operating regions, we have this hybrid controller. So altogether, we showed that behavior trees in this way form discontinuous dynamical systems. And here we have an example of a pendulum swing up task. You don't really have to understand what this is, but you can see that there's two distinct regions here. Around here, around the intersections of these dashed lines, there's a region where the vector field behaves a bit differently. That's where this linear feedback controller is used. And then for the rest of the state space, energy-based controller is used. So you can imagine in an AV, if you have multiple different controllers that act in different ways, you can form a discontinuous vector field like this that enforces convergence for like multiple different tasks together. Right, so now that we've formulated, or now that we've shown that behavior trees are discontinuous dynamical systems, we're able to prove existence and uniqueness, which basically means that execution of the behavior tree controller will have a solution that you can analyze. So there's like some different cases here that your vector field needs to satisfy with the behavior tree. So yeah, in A and B, the vector fields point in the same direction over the boundary of each subcontroller. And then in D, the vector fields can actually point towards each other. In that case, you have what's called a sliding mode solution, where the vector fields kind of combine in sort of a unique way. And then in C, there's no unique solution. So if your behavior tree controller with your given dynamical system satisfies these characteristics, then you'll have unique solutions. So then we also analyzed convergence of these behavior tree controllers. And we did this with the inspiration of some works from sequential composition, which started in 1999. So on the left here, you have a picture of two funnels. And if you're familiar with control theory, these kind of look like Liu-Punov funnels. So basically what this is showing is the region of attraction of different controllers. So you can imagine this funnel on the top is illustrating the region of attraction of a controller, which means that if the system is within, or if the state of the system is within that funnel, then it's guaranteed to go down that funnel. And so if you piece all these funnels together, or all these different controllers together, then you can guarantee that all the controllers together will enforce convergence to some goal state. And that's what you see here on the right. You can put them all together, even with multiple different paths, so that you can get to a goal. So you can think of this as achieving a bunch of different sub-goals in order to get to an overall goal. Yeah, and so we showed this with behavior trees. So in the example I gave earlier with the eating food in the kitchen example, we have this traversability graph, which basically shows the switching between different controllers. So it can be interpreted like this. So if you're in operating region 1 in the running region, then you're trying to go to the kitchen, and eventually you succeed. And then in operating region 3, then you're trying to turn on lamp A, or you can try to turn on lamp B. If you try to turn on lamp A and lamp A fails, then you can try to turn on lamp B. And yeah, there's like multiple different ways to get to successfully eating food, which is this region here. Yeah, so basically the theorem that we have in our paper says that this graph needs to be acyclical, meaning there's no cycles, and all the sinks or the endpoints of the graph need to be in success regions. And yeah, there's a lot more math involved there, but that's the high level description of it. So just to reiterate the conclusions, it's the first continuous time formulation of behavior trees in the form of discontinuous dynamical systems. And we proved existence and uniqueness of the solutions of these discontinuous dynamical systems. And we also proved convergence for general behavior trees, not just specific designs. There's been some papers before that have proved convergence for specific behavior tree designs, but the theorem that we present here actually proves it for general ones. So it can apply to any design. And ultimately what this enables is the application of continuous time control theory to behavior trees. So like continuous time optimal control, continuous time like sliding mode control. There's a bunch of literature on that. Okay, and so for the ongoing work, what I'm working on now is applying this general theorem to popular behavior tree designs in robotics, so I can kind of ground the theory in more of a robotic context, just to illustrate it more. And one of those popular behavior tree designs is actually backchain BTs. Backchain BTs are like these behavior trees that you generate online. So you can imagine like if all of a sudden you have a different AUV mission, you can generate a behavior tree online. And basically what we want to show is that we could use this convergence theorem to generate behavior trees that are convergent. And we want to be able to do that online. And also we want to prove cyclical convergence. So sometimes in behavior trees, you might have cyclical behavior, like sometimes in AUV, or a lot of the times with AUVs, when you want to survey an area, eventually you're going to run out of battery. So you might have the situation where you need to survey, and then once you're getting low on battery, go back to charge your battery, and then go back to surveying. So that would be a cyclical behavior, and that requires a bit more theory that we're trying to develop now. But it's in the works and it's coming soon. And then with all this theory, we want to be able to optimize behavior trees. So there's two things that need to be considered with behavior tree designs. It's first, the structure of the behavior tree. So that's like the ordering of all the actions in the behavior tree. And then also the actual nature of the controllers in the behavior tree. So those are two distinct things. Actually, it's kind of a bi-level optimization. So yeah, you have to optimize the structure and then optimize the controllers. And those things need to be optimized jointly. And that's also what we're working on. So we hope to apply that in sort of a reinforcement learning context. So we can kind of learn what the optimal behavior tree is. Yeah, that's it. Thank you. Yeah. Yeah. Yeah, exactly. Sorry. Policies, yeah, policies means the same thing as the low-level controller. No, yeah. But so all your work so far has been only focused on the structure. Yeah. Well, no, it's both the structure and the policies, but we're just proving the conditions under which the structure and policies will lead to convergence. And yeah, in order to optimize those two things, that requires a bit extra work. Yeah. I can see how you switch between policies, right? Yeah. To reach a goal, and my understanding of all these last engineers is that you can, when you say I can put convergence of BTs, it means that even a BT design in a goal, you can prove that BT can achieve a goal. Yeah. But and that is again taking into account all these policies. All these policies are defined, and with this I mean when you say it's full, that's in the policy, right? So it doesn't involve an actual solver. Reaching out and driving the it could be, you could put a whole nother behavior tree right there. Okay. But yeah, so if we, so say eat food is like some continuous time controller. If we change the nature of that controller, then that's going to affect the performance of the behavior tree. Similarly, if we reorder any of these behaviors in a different way, that's also going to affect the convergence. Yeah. 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 Yeah, exactly. Yeah. So yeah, something I guess something left out is that yeah, like each controller needs to satisfy that in finite time it will invoke switching to another controller. Yeah, it's an assumption, but it can be reasonable. Yeah, because depending on the region of attraction of each controller, that region of attraction is going to make the trajectory of the system go in a certain direction. So yeah, but so that the switching that is invoked by that region of attraction for each controller needs to make an acyclical graph like this. So like you see here, like, yeah, I mean, it's just kind of like that. So like if you just look at controller G here, you know that in finite time it will be in J. And so if you apply that to every one of these controllers, then you end up with this acyclical graph. Yeah. So for each controller, if you know that in finite time it's going to switch to another controller, then you can basically add up all those things. Yeah, you assume, but if you actually have a real Liouville function, especially one that proves exponential convergence, yeah, then you can actually determine a finite time. Or I mean, you can prove an upper bound on the finite time that it switches, and that's useful for things. But yep. Yeah. Yeah. Yeah.
But have you considered also, like, if you want to take this whole thing and compose different entities to get your together? You're trying to solve an optimization problem in each step, or have you thought of that area of thinking, like, to combine these together into one big optimal controller or something like that?
Yeah, exactly. Yeah, you can do that. I mean, there's a lot of literature on optimal control of hybrid systems. And yeah, and I mean, this is actually a hybrid system. A discontinuous dynamical system is like a subclass of hybrid system. So all those methods could be applied to here, but the difference is the variables that we can manipulate are a little bit different. So like we have the structure of the tree and then the actual nature of the policies. So, I mean, you could just leave the structure of the tree constant and then train the controllers such that they make this convergence happen. But then, yeah, there's also potential in changing the structure of the tree itself. So those two things we think should be considered jointly. It should be like a joint optimization problem. Change the structure of the tree and the nature of the controllers simultaneously, such that they make this convergence happen. And yeah, we haven't figured out exactly how to formulate that, but we're working on it. Yeah.
It might be like finding the right method to solve that optimization problem might be a bit of a fun task, I guess.
Yeah. I think it might involve. Oh yeah, I mean. Yeah, there's stuff on genetic algorithms, but the problem there is that you're kind of losing, or you don't have a gradient there. So it could be cool to have the whole behavior tree be like one differentiable object, so that you could just like optimize it. Yeah, with jacks or something. No. So yeah, that's something else we thought of actually. So, well, it's been okay. So, have any of you guys used the PyTrees library in ROS? No. Okay. Well, so the behavior tree we have here is a discontinuous dynamical system. So it just looks like a vector field like this, but in order to make it equally as expressive as a finite state machine, then we need to add the blackboard. Like, it's called blackboard in PyTrees, but that would be like a separate container of discrete variables that the whole behavior tree has access to. So in order to make this equivalent or equally as expressive as a finite state machine, then we'd have to formulate this as a full hybrid system. So yeah, basically we would just add that blackboard through this formulation. And that's something we're considering doing. But yeah. No. A behavior tree is equally as expressive as a finite state machine if the behavior tree has internal variables. So the internal variables would have to live in the blackboard, which is what PyTree is called. Yeah. Well, we want to start small first, and then because once you start adding these internal variables or like discrete blackboard variables, then you have to start delving into hybrid system stability stuff, and that's kind of like the next step. So we can take this stuff and kind of build on top of it. So, well, no, it's still shown that the behavior trees are optimally modular. So yeah, it reduces cost of development and testing, makes it more interpretable. Like with SAM, if we used a finite state machine, it would just look like a bunch of, it would look like a spider web. It would be kind of hard to interpret. So there you can already see one benefit of using behavior trees. but the underlying thing that they represent is the same. They're both hybrid systems. So a behavior tree and a finite state machine are just two different ways to represent a hybrid system. So, but we're curious to see whether this optimal modularity of the behavior tree representation might mean that it's easier to learn something from. Because optimal modularity means that computationally it's less complex. So maybe that means that it's easier to learn from. I don't know. We're looking into that.
On the switch one way, can Zeno happen? Or do you know how to invent behaviors?
Zeno could happen, and additional analysis is needed to determine if it will happen. Yeah.
Yeah. So we can move on. Okay, thanks.